Okay, here we are doing a presentation on the lab experiment, The Case of the Drowned Businessman. So, I'm Sarah Greenbaum, and this report the data was garnered in conjunction with Henry Collett. Alright, so the objective of this was first off to construct a calibration curve using phosphate solutions. The phosphate was combined with ammonium molybdate and stannous chloride so that the phosphate would be visible to the spectrophotometer, so it was able to be measured. Alright, so we make the calibration curve and then we graph it with the percent absorption on the y-axis and then the concentrations on the x, and then fit a line to it, and then the slope of that line is the proportionality constant. We'll get to that later, why that's important. Alright, so then we measure 5 water samples, and I'll get to the backstory in a minute. So it's 4 lake water samples locally. It's Reservoir Park, Lake Pinehurst, Wood Lake, and Seven Lakes. And then 1 autopsy sample, and the sample that I used was the red sample. Alright, then you calculate the concentration of phosphate in those 5 samples using Beer's law and the proportionality constant determined by your calibration curve. And then you determine of those concentrations of phosphate which one of the standard lake water samples is closest to the 1 autopsy sample. Alright, so just a little bit of background information first. So the premise of this experiment is that a gentleman was found dead on the side of a road in, I believe, Robbins. His hair and clothes were completely saturated with water, and upon autopsy it was determined that he had drowned. So he wasn't near a body of water up in Robbins, so they looked at the water in his lungs and they found that it had a really high phosphate concentration. So they sampled lake water from the surrounding areas, those 4 lakes I mentioned, Lake Pinehurst, Wood Lake, Seven Lakes, and Reservoir Park, and so we are looking at phosphate concentrations. Alright, and one method by which we do that, or the method that we're going to use, is to use a spectrophotometer. The kind we use in class is an older model. It's called a Spectronic 20. And the purpose of a spectrophotometer is to measure the absorbance of light in a sample. So this allows a single wavelength to be passed through a sample. In this case, we use 710 nanometers. And again, this is off of visible light. Alright, so this percent absorbance measured, or the amount of light that a sample absorbs, so that's the goal for each sample that we measure. Alright, so specific things about this machine. You set the wavelength to 710 nanometers, so you turn the little knob and the little 710 pops up. You also allow the machine to warm up, the lamp in it to warm up for about 15 minutes prior to use, and also be nice to it. It's delicate, don't slam it around, don't break it. Alright, so here's that Beer's law I was talking about earlier. So, Beer's law states that A, which is the percent absorbance, which we measured with the spectrophotometer, is equal to B, which is the proportionality constant determined by the slope of the calibration curve, times C. And that's the concentration of the compound of interest in parts per million. In this case, it's the phosphate. So, absorbance is directly proportional to concentration. Alright, and that proportionality constant we gained from this data. So, these 5 standardized solutions that we made using the phosphate solution and then added the ammonium molybdate and stannous chloride in varying concentrations. So the idea is the more concentrated the sample is, the more light it absorbs. So as you can see, as concentrations increase, so do the amount of light it absorbs at 710 nanometers. Alright, it's a little hard to see. I probably shouldn't have used yellow. But you can see on the bottom here, this is the concentration in parts per millimeter of our standard solutions. And then over here we have our percent absorbance. And nifty difty Excel made me a line there. You can see the equation of the line fit to that data is y equals 0.2424x minus 0.0508. And that 0.0508 is the y-intercept there. Okay, so, I'm sorry, rather, it's the exit step. Alright, so what we're looking for most out of that equation is what the slope is, and that's at 0.2424. And that is equal to our proportionality constant, which is going to help us out a lot in Beer's law and calculating subsequent things. Alright, so we take our 4 water samples, Wood Lake, Lake Pinehurst, Seven Lakes, and Reservoir Park, and we measure the percent absorbance of each of them. And then we have our autopsy sample. So this is water taken from the lungs of the drowned businessman, and my sample was the red unknown. All right, so you can kind of, because it's directly proportional, it's pretty easy to guess from the data, but also I have our calculated concentration values on the right in parts per million. So I put them in bold, what I think our answer is going to be. So let's skip over to calculations here. All right, so a sample calculation. Because I suspect it's Lake Pinehurst, see that percent A, or A, is 0.716. All right, so A equals B times C. So A is 0.716. And then we have our proportionality constant as determined by that calibration curve. The slope of that line for the calibration curve is 0.2424. So it is 0.716 equals 0.2424C. Divide both sides by C, or I'm sorry, rather, divide both sides by 0.2424 to equal C, and you get 2.95, and then the units for that, for concentration, is parts per million. So we already pre-calculated that one. We'll go back here and we'll see we put in 2.95. And then, because we're interested in finding out what the concentration of the red sample is, the phosphate concentration, and using the same equation, we come up with 3.07. And then in relation to the other values, 1.64, 4.13, and 2.45. 2.45 is kind of close, but not close enough. So we're going to go with the samples from Lake Pinehurst and our businessman drowned in Lake Pinehurst. All right, so our discussion. We use the calibration curve to determine that proportionality constant. So we take known concentrations, that 1, 2, 3 through 5 parts per million, and measure the percent absorbance for each one. Slope of the line equals your proportionality constant. Then you have that direct relationship between absorbance and concentration with the proportionality constant in the middle. So then you have your A equals B times C. All right, we measured the absorbance of the water sample, so that gives you an A. Then we use Beer's law to calculate C, given that we already have B from our calibration curve. So, and then we compare to determine the origin of the autopsy samples. And Lake Pinehurst, 2.95 parts per million, the red sample, 3.07. So one thing it asked for in this experiment was to determine a source of error for this, and human error doesn't count, which there's human error in almost every experiment. So for this, the source of error I selected, so phosphate is not visible to the spectrophotometer at the wavelength that the spectrophotometer transmits light. So we have to find a way to make it visible. So by putting in that ammonium molybdate and the stannous chloride, it turns the solution a bluish color, kind of like a smoky blue almost. Obviously it gets darker the more there is in there. But if you don't allow that solution, the directions say to let that solution develop or that reaction to proceed forward for approximately 5 minutes before you stick that cuvette in the spectrophotometer. So if you shove that sample in the spec before it has time to fully develop, then you won't be able to see all of the phosphate that's actually present in that sample. So patience is key there. Okay. Conclusions. Businessman drowned in Lake Pinehurst. The phosphate concentration of the autopsy sample in red matched most nearly to Lake Pinehurst. So, avoid Lake Pinehurst. Thanks.